Okay, welcome back. So our next tutorial talk will be given by Professor Reza Gheissari from Northwestern. He will tell us about Ising Dynamics, mixing time. And just a note, because this is remote, so unless you're using the microphone, the speaker won't be able to hear you. So if you have any question, raise your hand and I will pass down the microphone. Okay, so Reza, the stage is yours. And, please go ahead.
All right, thanks very much. Yeah, thanks all for listening in, and I'm sorry to not be able to be there in person, but really thanks for the invitation to give this talk. So I just want to preface, I don't know too much about quantum, but I hope that this foray into classical mixing times is interesting and useful, and I'm very happy to hear about how the relations. So I'm just gonna give a kind of overview talk on, mixing times of Ising dynamics is a pretty broad field, but I'll talk about some techniques and try and give an overview of where the field's at these days. Please feel free to interrupt at any point, and I'm happy to answer any question. So let me just start off with defining the Ising model. So the Ising model is a probability distribution over a state space, and the state space is assignments of plus minus 1 to the n, where n is the number of vertices usually of a graph. And so the probability assigned to a state is, I'll write it as pi of sigma for now. So sigma is an assignment of plus minus 1, is proportional to exponential of minus beta times some Hamiltonian, which I assign to the configuration. So that's the energy of a configuration. And h of sigma takes the form, we have something, usually it's of this form, I'll write it like this, jij, sigma I, sigma j, and maybe there's a linear term, which is an external field term. So here's a little picture of an Ising configuration. So we have a grid, and for the most part, I'm going to focus in this talk on situations where there's an underlying graph. And so let me say maybe the classical or the ferromagnetic model. Ferromagnetic model is when the Jij's are all positive, and maybe J is the adjacency matrix of a graph. J is adjacency matrix of a graph G. And so for the most part in this talk, I'll think about G as being a subset of Z2 or Z3 or ZD, but a lot of the things that I'm going to say extend to the case of much more general graphs. And I just want to make a few points just about what this distribution looks like. So in this classical or ferromagnetic case, the J's are all positive. So the energy is, our goal is to minimize energy, and the energy is minimized by configurations where all states are aligned. So note, energy is minimized by sigma is all plus or sigma is all minus. And beta tells us how much we favor minimizing the energy. So beta is usually called the inverse temperature. Beta is an inverse temperature. And beta small looks very random. And beta large, the measure puts most of its mass on the all plus or all minus configurations. I puts most mass on configurations close to all plus or all minus. So I think probably a lot of the audience has at least heard of the Ising model before. And so this is the general, this is just the basic definition of the ferromagnetic Ising model. It's one of the simplest models of a phase transition coming from statistical physics, because as you vary beta, there's a sharp point for most graphs where you go from looking very ordered to where you go from looking very disordered to looking very ordered. And so it's seen a lot of attention in physics, math, all of these literatures over the years. Let me just note that there's one other, there's other situations that are also of interest. So for instance, there's the case where it's not ferromagnetic. So I just want to make a comment. So compare to Jij are normal 0 sigma squared, which is the famous SK model of spin glasses. So in the generality that I wrote above, this captures ferromagnetic, antiferromagnetic spin glass models. But for the most part in this talk, just since I'm trying to give, I can't cover everything that's been done in mixing times of Ising models, I'll focus on the ferromagnetic situation. Okay, are there any questions about the definition of the model? So then we want to introduce a Markov chain and think about sampling from this distribution. There's different ways to sample, but again, for the purposes of this talk, I'm just going to think about like the simplest local Markov chain. So I think I looked at a few of the talks or parts of the talks that have been given in this workshop already. And so I think metropolis dynamics, classical metropolis dynamics has already been introduced. So Glauber dynamics is very similar. So it's the following Markov chain. So so they're at each time step, one, pick a vertex uniformly at random. The in your graph uniformly at random. And then 2, resample according to stationary measure, so according to pi. Conditional on all other spins. So here's a simple picture. So at time t, the clock at this vertex v rings. This is the vertex v. And then there's 2 possible options it can take. It can change the vertex v to plus or minus. And it does that with probability proportional to exponential beta, the number of neighbors that share the same color. So here the probability would be proportional to exponential 3 beta, and here exponential minus beta, let's say. Well, 3 and 1, I guess. So exponential beta. So it has 3 blue neighbors and 1 red neighbor. And so when it resamples according to the stationary measure, it does so with probabilities proportional to these. You can also define, so this is the discrete time version.
There's a question.
Yes?
That's a question.
Yeah.
So this particular version of the Glauber is called heat bath.
Yes.
And is there some difference between the analysis using the heat bath version or the chain version? So the other version.
So for instance, like Metropolis or something.
Right. Yeah.
So in all the situations that I've looked at, or for Ising models, for instance, the probability of the transitions for the 2 Markov chains are comparable by a universal factor to one another that only depends on beta. And so there's just a constant factor difference in their mixing times and things like that. So you can do a simple comparison between 2 Markov chains that have the same stationary distribution if their transition rates are within a factor of each other to say that the mixing times are the same up to a factor.
A factor in the exponent? Like
No. Just an order 1 multiplicative factor.
I see. But the heat bath version is easier to analyze.
Honestly, they make essentially no difference in any of the analysis I'll tell you about.
Thank you.
Yeah. So I can also define a continuous time version of this. Continuous time version, where I just step 1 becomes assign each clock a Poisson, a rate 1 clock, assign each vertex a Poisson clock. 1 becomes assign each vertex rate 1 clock. And then whenever the clock rings, you resample according to the same step too. So this Markov chain was introduced by Glauber in like the 1960s to analyze the out of equilibrium dynamics of statistical physics systems in contact with some kind of heat bath. So that's giving the thermal energy to make updates. And importantly, this is reversible, so it satisfies the detailed balance conditions with respect to the stationary measure, which is pi. So it's reversible with respect to pi, which I defined on the previous slide, so the Ising measure. So as a consequence, as t goes to infinity, so as t goes to infinity, the time of the Markov chain, the law of the chain, which I'll denote by xt, converges to pi. So this gives an algorithm for sampling from the distribution, and if I run it for long enough, and the real question that we're interested in is how does the time that it takes to equilibrate scale with n? So the real question is how does time to be close to pi scale with n? And this depends on beta and the graph. On beta and the graph family underlying things. Okay. So if I can promise you that this time to be close to the stationary distribution in some sense is polynomial, then that provides me with a polynomial time algorithm to output a good sample from the distribution, and I'm happy. Okay. So let me be a bit more precise about what I mean by this and introduce the notion of the mixing time. So the mixing time of a Markov chain, mixing time, is defined as follows. So T mix is the first time such that no matter what initialization I started with, so that's what this max over x0 will mean, my total variation distance, so the law of the Markov chain at time t, given it started from state x0, 2 pi is less than, let's say, 1/4. But really less than some small epsilon. You can define a total T mix for that epsilon. And an important property, so the reason why it's sufficient to put 1/4 here is that after the total variation distance has gotten below 1/4, then the mixing time satisfies a nice boosting property in that this total variation distance here, so this decays exponentially with rate t over t mix. So in particular, it's i.e. it's at most e to the minus some universal constant times this. So once I've weighted the mixing time, then if I weight a multiple of the mixing time, I can get this total variation distance arbitrarily small. And so if you want it to really be like essentially nothing, so exponentially small, you just need an extra n factor in how long you wait or how long you run the Markov chain. So this mixing time with just 1/4 captures like the time you need until you're able to contract the distance to stationarity. This is closely related to other notions of equilibration time that you might be familiar with, like inverse spectral gap. So this is closely related to spectral gap, maybe inverse spectral gap, which is essentially the same as a Poincaré inequality for the distribution. Log Sobolev inequalities quantities, and maybe even modified log sub 11. So if you've heard of these concepts, then the mixing time is closely related to them. If you haven't, just ignore that and focus on the mixing time. Okay. Are there any questions at this point? Okay. Let me give the phase diagram for what's known about the mixing time of Ising dynamics. So I'm explaining this phase diagram as it's known for, let's say, ZD. So subsets of n vertices in a box in ZD. So at high temperature, it turns out that so at high temperature, the mixing time I'll write the mixing time in discrete time. So you have a discrete time Markov chain is an optimal n log n. So even in a product measure on the hypercube of dimension n, you can't do any better than that. So that's the n log n. At criticality, so let me give a brief history of this. So this is saying that the high temperature measure, so a typical sample at high temperature looks like this. It looks completely chaotic. There's not a long range ordering of the pluses and minuses or of the blues and the reds because the entropy wins over the two ground states or the phase structure of the model. And so what this mixing time guarantee is saying is that in that regime, you're able to treat the Markov chain as close to a product chain. And so even though things aren't actually independent, they're sufficiently independent at long ranges. And I'll give a sketch of how this is proved. So this, the history of a bound like this goes back to Martinelli and Olivieri. So let's write Martinelli, Olivieri in 94. Then a log Sobolev inequality was proven by Chasey in 2000. There's some more refined analysis that I'll talk about by Dyer,
Sorry,
Sinclair.
the color doesn't show up nicely. Maybe you want to change something
Okay,
darker.
thank you. Yeah, so this is that better?
Yeah.
Or should I stick to the
slightly?
Okay, this is better.
Oh yeah, this is much better.
Okay, thanks. Martinelli, Olivieri in 94. Then Chesney in 2000 showed a log Sobolev inequality. Again, if you know what that is. And then so there's lots of works refining these kinds of analyses, but there was work by Dyer, Sinclair, Vigoda, and Weitz that I'll talk a little about their argument in 2002. Mosel and Sly showed that on all D-regular graphs, you have n log n mixing up to some tree uniqueness point, which is like the critical point on a tree. That should not be there. Okay. And if you've heard of the notion of cutoff, which is pretty central in the Markov chain mixing time literature, then there was a big breakthrough by Lubetsky and Sly in the early 2010s showing cutoff, which says that you can identify the exact prefactor in front of the n log n. So that's C star n log n for the mixing time. Okay. At criticality, it's believed that the dynamics slows down polynomially. So it's still polynomial, but there's a slowdown. What happens in criticality is that there's some influence that permeates through the system, but it doesn't go all the way out to infinity. So far apart points become decorrelated as they get further and further away, but the correlation distance is kind of, it can be unbounded. And so in dimension 2, Lubetsky and Sly showed polynomial, showed poly of n. And in dimensions at least 5, in recent work of Bauer-Schmidt and Dagalier of last year, they showed poly of n. So the dimensions 3 and 4 critical Ising model remain open. And then at low temperature, the picture completely changes. So the fact that there's the two ground states makes this is kind of, I've made a schematic of the probability function. Of course, it's a function in n-dimensional space, but I made it a 2D function roughly. And the landscape looks bimodal. So there's two dominant phases. This I'll call the minus phase, where most sites are blue, and then there's a plus phase where most sites are, the minus where most sites are red or minus, and a plus phase where most sites are blue or plus. And these two coexist, and it takes a long time to transit in between them. So exponentially slow mixing. And just to give a few references, in dimension 2, this was known from work of, I think, Chase, and Schoenman in 87. And in general dimension, getting it all the way up to the critical point, this was work of Bodino and Pistora. '05 and 96, something like that. Okay, so you have this transition in the model, just like in samples of the model. The distribution has a phase transition from high temperature to low temperature, where it goes from disordered to ordered. And what that induces in the dynamics is it goes from fast mixing to slow mixing. And so I want to talk about some techniques that are used to show fast mixing in this model, and maybe a little more in like some more interesting, more modern directions after. Any questions about that?
So I have a question on the mixing time. So the n log n is the mixing time for discrete time chain, right? So
yeah, so it
I
would
think I'm
be
asking for the
log
continuous
n.
time chain, it will differ from n factor. Is it correct?
Yes, that's right.
Okay. Thank you.
Yeah. So at high temperature, it's really optimal mixing. There's a order 1 spectral gap, log n continuous time mixing, and the extra factor of n. This factor is only from the discrete timeness. And at criticality, it truly slows down. So when I say it's polynomial, that means it's slower than linear by a polynomial.
Near the criticality, I mean, these are polynomial, but how do they depend on the distance between beta and beta c?
They blow up polynomially as beta goes to beta c. So it's basically equivalent to show that it blows up polynomially and as beta goes to beta c, as to say that at beta c it's polynomial. Okay. Any other questions? All right, so let me talk about some techniques that appear in proofs, especially of the fast mixing guarantees. You know, we want polynomial time methods and fast guarantees, so I'll talk about some different proofs. So I'm going to split how I present this into kind of two sections. So one is what I'll call classical arguments, and then I'll talk a bit more about what I'll call modern arguments, maybe. So the classical arguments are really focused on doing some kind of space-time recursion. And so you do some kind of space and or time recursive analysis. And what the type of theorem that you want to get out of this is that influence decay, so that's like covariance of sigma x and sigma y going to 0 as distance of x and y goes to infinity, implies, so influence going to 0 implies fast mixing of Glauber. So that's the type of goal that there is. So let me sketch out how one such argument would go. So by now there's tons of different arguments that rely on different kinds of space-time recursions and things to get either spectral gap, Poincare inequality, coupling, things like that. But roughly speaking, I can say that the model has some kind of spatial mixing property. So this is not about the mixing time, but about influence decay. So define spatial mixing if the total variation distance between the law induced by a box with plus boundary on maybe it's like inner on some vertex in the middle or it's marginal on this region. So this is the law induced on the middle region. Maybe I'll use a different color. So the law induced by this box on the middle region versus the law induced by red boundary conditions on that same middle region. And let's call the width of this box R. If this total variation decays exponentially in the size of the box, then I say that the model exhibits spatial mixing. And so this holds at all high temperatures. So this holds when beta is less than beta C. And so the type of argument in this high temperature regime is to show that this kind of influence decay implies fast mixing of the Glauber dynamics. Okay, so how does that go? So proof, so I guess I'll say theorem is spatial mixing. This is informal and due to many people. Spatial mixing implies n log n mixing time. Okay, so let me give us idea of the proof. So here's the proof idea for you. Proof idea. The goal is to reduce scale. So I want to show that if I have this kind of influence decay, then I can compare the mixing time on the n by n box or on a box of n vertices, let's say, to a box with side length log n, so polylog vertices. So goal is to reduce scale. So the first observation is that the total variation distance to stationarity can be bounded by the total variation between two chains, one of which is started from all plus and one of which is started from all minus. So important to this argument is a monotonicity property. So monotonicity, which says that if I start from all plus, because the model is ferromagnetic, it is the most plus possible Markov chain is the one started from all plus, and the most minus Markov chain is the one started from all minus. So monotonicity implies it suffices to bound the TV distance of xt start given x0 is all plus and xt given x0 is all minus. So if I show that, if I can bound that total variation, then I've sandwiched everyone in between. And this total variation is bounded basically, well, I can say in order for me to couple these two Markov chains, it suffices to say that I've coupled on every vertex and do a union bound. So a union bound reduces, so I'll write this like this. Probability that xt plus is something, so the plus in the superscript means started from the plus configuration, minus probability of xt minus. This total variation is bounded by n times, let's say, the worst vertex, the marginal at that vertex. Okay, so I can reduce to the single site marginals of the two Markov chains and just argue that up to a factor of n, if I get the total variation distance, so the probability of not coupling at any given vertex to be small, then a union bound suffices. Okay, now if I have two Markov chains, it's again, if I freeze the boundary, so take a box around the vertex V and freeze the boundary outside of it in one of the Markov chains to be all plus and one of them to be all minus. That freezing only makes the plus one more plus and the minus one more minus. So I can sandwich the two Markov chains by the ones which are localized. So I can sandwich xt plus and xt minus by Markov chains on O of log n boxes, sized boxes, centered at V, at the vertex V. Okay, and so let me make room for myself here. Are there any questions about this so far? Okay. So now that I've localized things and I've reduced to a smaller box size, I want to say that if I couple on the small box, then now let's finish the argument from there. So if t, so the time that I wait, is much bigger than the t mix at scale order log n, then the Markov chains which are on the small boxes can be treated as stationary samples. Then the localized chains on the O of log n sized box mix in that time. And the spatial mixing property, so high temperature, spatial mixing, implies their stationary measures are close to each other. Distributions are at most exponential of minus some c log n, which is at most n to the minus 10 apart. So together that means that the Markov chain started from all plus and the Markov chain started from all minus at the vertex V differs by at most n to the minus 10. So because of that, I get that. So if I come up here, thus this is at most n times n to the minus 10, which is little o of 1. And so that's basically the argument to tell you that the mixing time of a n by n box is bounded by the mixing time of a log n by log n box, with a maybe incurring a factor of log n or something. Now I can recurse this. I can do this over and over and reduce the scale of the log n box to a log log n sized box, and the log log n sized box to a log 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 sized box, all the way down to order 1. And so that proves essentially optimal mixing. So if the mixing time isn't dilating much when I grow my box exponentially, then that means that the mixing time is small. So this is the idea of like a spatial or space-time recursion to bound the mixing time. Are there any questions about that?
Can you be a little bit more specific? I mean, here you have this log n mixing time, right? I don't see how I mean, how the at the end you should have n log n, right? How this n comes up? Maybe you can go a little bit deeper into this recursion argument.
Sure. So okay, let's so take everything in continuous time. So then you should expect log n as the mixing time. Okay. If I do everything in continuous time, when I say here in this step here, I said if t is much bigger than t mix, then I can treat the samples of the Markov chains on the small box as stationary. So there, that really means if this is, so I'll rewrite this portion. If t is at least some c log n times t mix at scale order log n. So I incur a factor of log n there because, as I said in the previous slide, the mixing time, the total variation to stationarity decays exponentially beyond the mixing time. So if I throw in this extra factor of log n, then everything up to polynomial error, which can be union bounded over, can be treated as truly stationary. So in conclusion altogether, the mixing time at scale n is bounded by log n times the mixing time of a box at scale log n in continuous time. The log n one will be bounded by log n times the mixing time on the log box. And so if you recurse on this, you'll end up with something like, so the conclusion of this will be t mix continuous time is at most log n to the 1 plus little o of 1, let's say. And then there's a boosting argument that's not too hard to boost that up to optimal mixing. Okay. So that's this kind of argument goes back a long time. Is there another question? Yes.
I think I want to ask a more intuitive question. So, in the beginning, you mentioned like more monotonicity.
Yes.
Like, it seems this property is very important in the proof. Like, can you give a intuitive explanation why this is important?
Yeah. So the intuitive explanation is that if I can't sandwich the other Markov chains between the ones with plus boundary that are closer to you and minus boundary that are closer to you, then locally near you, the boundary conditions are changing. And so I'm not able to do this scale reduction in the way that I described. Now, there's other tools for handling situations where there's not this kind of monotonicity. But some, there are big problems with getting proofs of certain things without monotonicity that you can prove with monotonicity. So I chose to present this, which is maybe the most classical argument for Ising. But the monotonicity is used to put frozen boundary conditions locally near you. Okay. Let me say a word about the low temperature regime now. This got moved to here somehow. Okay, so in the low temperature regime, the first thing I'll say is it takes exponential time to transit from what I'm calling the minus phase, which is when the majority of sites are minus, to the plus phase where the majority of sites are plus. So there's an exponential of n to the, I guess it's not quite n, but it's n to the d minus 1 over d bottleneck to go from mostly minus to mostly plus. So this follows by kind of analyzing the probability of having a near even split of pluses and minuses versus having a dominant phase. And so as you can see in this this is like a free energy landscape. It's it's very small at the cut in between these. So that's a bad cut that's hard to traverse. So I don't want to say too much about slow mixing, but there's some interesting questions that one can ask about the low temperature regime still. In particular, there's a folklore belief that can be formalized in different ways that mixing within one of the phases should be fast.
Can I ask a question? So bottleneck means lower bound of T mix.
Yeah.
And this is established with some energy barrier argument.
Yeah, you just say like probability of the boundary of the plus phase over probability of the plus phase is exponentially small. So it's a purely stationary thing. So boundary of the plus phase is you have a balanced number of pluses and minuses, and the plus phase has probability 1/2. If a majority plus has probability 1/2 just by symmetry. So this then becomes something about the equilibrium distribution of the model.
Bottleneck is kind of a cheek argument.
Yeah, exactly. But there's a folklore belief that mixing inside a phase is fast. So this is a bit informal, but you can think that if you restrict the configuration to maintain a majority plus, for instance, then the Markov chain that's restricted to do that should be fast. So e.g., if I restrict the Markov chain to keep majority plus. So this isn't actually true if I state it like this. So this is not actually true. There are bottlenecks even inside of a phase. There is slow mixing even within a phase when I'm on the lattice. But there's two maybe versions of this that I can state more mathematically formally. So here's the more formal mathematical conjecture, which is this is a very famous problem in the field, maybe one of the biggest problems in the field, is if I put boundary conditions at low temperature, most things want to be plus in here. And so this kind of destabilizes the bottleneck and makes it so that it should look more like this. So this is plus, and the minus phase becomes unstable now. And so it's believed that this here, so the conjecture is T mix of a box with plus boundary conditions is polynomial. Is poly of n. And the best known, in fact, it's something like n squared in continuous time should be what you expect. And the best known is n to the log n in dimension 2 and exponential in dimension at least 3. And this is due to, maybe I can. So this is due to the progress that I mentioned there is, or what's known that I mentioned is due to Lubetsky, Sly, Martinelli. I think that's not working, but okay, Martinelli and Toninelli in 2012. So there should be some notion that if I restrict to a phase, even though there's phase coexistence and a bottleneck, if I restrict to a phase, it's fast. And so that's one form of this, is by restricting to the phase by putting on boundary conditions. A different form, like I said, is just by restricting the Markov chain, but I said it's not actually true. So here I can mention a theorem of mine with Alistair Sinclair. So this is a theorem from Gheissari and Sinclair in 22, we showed that the Markov chain restricted to the plus phase, and initialized from all plus is indeed fast at all low temperatures. So on the previous slide, I said you can consider the Markov chain restricted to one side of this picture, let's say the right-hand side. So it rejects any update that takes it outside of the majority plus. That Markov chain will not be fast from arbitrary initialization because there's some other bottlenecks in this picture. So there's some other wells around this picture. But if I start from a good initialization, like the all plus one, then the mixing time is fast. Yeah, there was a question.
Yeah. So can you comment on for the D is bigger than or equal to 3, that exponential mixing time is also expected to be sharp or not, because the boundary is just
Over
in higher
here?
dimension is not large enough.
Which
Just to understand the setup. The setup is you fix the boundary to be all plus and
Yeah.
ask what is the mixing time in this constrained case, right?
Yes.
So do you think that for D is bigger than or equal to 3, I mean, there should be a lower bound of exponential, or
No. The conjecture is it's polynomial with the
they're all
plus bound.
polynomials.
Always polynomial. The upper bounds are just terrible. And this has been a major open question for the last, I don't know, 40 years at this point in there, or 30 years in the area. And in dimension 3, you can't do any better than the exponential in like d to some power, n to some power.
A lower bound.
Any other questions? Okay, so just very briefly, proof idea of this, so proof idea here of our paper. So this was, you look at the regime where there are 2 phases, but you restrict the Markov chain to one of them. If you start from the ground state, which in this system is easy to sample from, or something that's close to the ground state, we can show that indeed you do mix quickly, restricted to the phase. And the proof idea is adapt the high temperature one. So the one I said of a space-time recursion. And what you need is the key ingredient is you have some kind of influence decay or spatial mixing between plus boundary on a box and mostly plus boundary. I'll put quotes around it. So this is, let's say this is sampled from the phase, the one on the right. So it's got mostly plus, but it's got big chunks of minus also all around it. But most of the areas are plus. And so we were able to show that these 2 measures, their total variation on the inside is not too far. So if I look at the marginals they induce on the far away from the boundary, then that decays exponentially in CR, where R is this distance. And then you can kind of push through the kind of space-time recursion of high temperature. Any questions on that?
Yeah, so how do you actually restrict it to the plus phase here?
Just condition the measure to have majority plus.
That's why you need to deal with the boundary being flipped.
What was it?
That's kind of why you need to consider the boundary being flipped in this influence decay.
Yeah, exactly. So the boundary, if I condition the big box to have majority plus, what we can show is that on a small box it will look like 90% plus, or some majority plus. And then you need to compare the majority plus boundary to the all plus boundary.
And the all temperature means that all the way to critical?
This is all low temperatures means, yeah, all beta bigger than beta C in every dimension.
How to physically understand this? Because for the high temperature one, you can think of the correlation function going from exponential decay to a power law. And for
Yeah.
the low temperature one, they're all, I mean, bad. And so how do you make use of this fact?
So if you subtract off the mean, so it's true that the correlation function is the correlations don't decay, but if you subtract off their mean, then you have exponential decay. And so it's like when I constrain myself to live inside of a phase, then influences do decay. But the problem is there will be places where the boundary is pretty minus by chance. And those are really bad. They're pushing you in the other phase. And so then you need to do some work. Okay. Maybe in the minutes that remain, I want to mention a different direction, which is more modern arguments, or what I'll call modern arguments, where instead of interpolating in space and time, which is kind of the long-standing approach to Ising dynamics, you do some kind of interpolation in the space of measures. So interpolate in space of measures instead. And here, the kind of terms that maybe you've heard of are stochastic localization as one approach to bounding mixing times, or spectral independence as another. And these have been used to go beyond either the monotonicity requirement or some kind of geometric requirements that the previous arguments required, things like that, and handle more general situations by not doing some kind of spatial recursion, which requires some consistency on the graph structure. So for instance, when I was recursing the box down to smaller boxes, that required consistency on the graph structure between scales. These kinds of arguments, since they're interpolating in the space of measures, they more need consistency in some other interpolation that's maybe easier to prove or easier to make use of. So I'll explain stochastic localization at a high level and how it can be and how it's used to bound mixing times in the next 5 minutes. So there's many different definitions. One of, the one maybe you're most likely to have seen is as an SDE in the space of measures. I like the following interpretation for an Ising system. So my goal is to sample from, let's call mu naught is pi. So this is my target mixing time distribution, or this is like the target distribution for which I want to prove something. And I'm going to interpolate from this to a trivial measure by first drawing. So one is draw a sample from the measure. And let me call y sub t. This is the just an n-dimensional stochastic process, which is t times this sample plus a Brownian motion. And then to define mu t, so mu t is the measure. So this t is not time of the Markov chain. This is time in the interpolation. Mu t is defined as the tilt of mu 0 by exponential yt inner product with sigma. So this is mu t of sigma, I guess. So I just induce a linear tilt. This is a linear tilt or an external field. Linear tilt, i.e. external field, in the direction of sigma star for the most part, but plus some noise. So here's a visualization. So I start with this initial distribution, mu naught. It looks complicated. I draw a sample from it, which will be like, let's say I took this point, and that was my sigma star. That was the point I drew. And then I'm just going to kind of increasingly put an external field that aligns my measure with that direction. But I do it with some noise. That's the Brownian motion part. But as time goes to infinity, T sigma star is much bigger than BT because BT is like square root T as T gets large. So what that means is that as time goes to infinity, it converges to a delta mass at sigma star. So as T goes to infinity, mu T converges to the random measure, which is a delta mass at sigma star. So this is IE, it trivializes the measure, in the sense that the final thing has no bottlenecks. So it has, if you did Glauber dynamics with respect to a delta mass, it's obviously fast. So now I just need to understand how bottlenecks or isoperimetry changes over time, over the process. And if I can do that, then I can get spectral gap or mixing time bounds on the initial measure. And the real magic here is that stochastic calculus and some martingale arguments, martingales, gives me that T mix of mu T's Glauber is at most exponential. Sorry. So this is, I need to make some room. Okay, it's at most exponential of something like the covariance matrix is operator norm. 0 to T, cov T op, times T mix of mu infinity, or of mu capital T. This is. So my goal mixing time, which is the left-hand side here, this mixing, is bounded by the mixing time of the Glauber with respect to the final measure times exponential of operator norm of the covariance matrix. Now, I don't need something like exponential decay of the covariance matrix or anything like of influences. I just need an operator norm bound. And that's easier to obtain. Yeah.
Ask here, the T mix is more like spectral gap version or the model?
Yeah, really, I'm lying to you a little. It's the spectral gap, not the mixing time and things like that. Okay, so
I think also there was a more recent paper by Reza and Eldon showing that Gibbs is also kind of like a stochastic localization, right? So, but this is not the version you are using here.
saying that what is also a stochastic localization?
Gibbs, the global dynamics can be also understood as a
Yeah. So that's right. So there's various different stochastic localizations. There's a whole literature. So I was going to mention a few of the works quickly. But yeah, so there's a big literature in this rough direction of interpolating in the space of measures that's really come alive in the last 5 years. But this is like a very, I don't know, in my opinion, an intuitive way of seeing it. And something really nice is this distribution stays an Ising model. It just has a random external field on it. Okay. All right. So let me just say, just very quickly, some works that are related to what I just said. So there's Bauer, Schmidt, and Dagalier use this for the dimension 5 criticality. So these are progresses due to this stochastic localization approach, and also critical easing on random regular graphs. Eldon, Kohler, Zaytouni used it, so 2019, this is 23, for the Sherrington-Kirkpatrick or SK spin glass to get fast mixing of the Glauber dynamics. And some other works to be aware of in this direction are Eldon and Chen on localization schemes in more general, and in the spectral independence direction, Anari, Liu, and Ovesh Karan. 20. Okay, and I just want to end with the big open questions of the area, and then I'll stop. So one
There's
of them
a
is
question
this
before
question.
that.
What was it?
I have one question. So at the end, you need to prove this bound for this covariance matrix, right? The operator non-bound.
Yes.
What goes into that? Does this usually need a geometric argument like what you did earlier?
Yeah, so then this becomes a model specific kind of thing, and that's where you use high temperature, and that's so at some point there needs to be some input that's using the high temperature structure, and the point is that in a lot of these models, for instance, at criticality in dimension 5, they were able to show that this thing here is logarithmically blowing up instead of worse, and so you get polynomial for the mixing time. Okay, so just to end with the open questions that I've mentioned. So one of them is T-mix with boundary conditions at low temperature. Should be polynomial, is poly. So this is, I have minus boundary conditions on this box, and this droplet of plus should shrink over time. The next one I'll mention is, this is one I especially like, is T-mix at low temperature. When I start from a uniform at random, started from uniform at random assignment. So this is a very noisy uniform at random assignment. That should break the bottleneck. So you have this double well. That should lead to you starting in the saddle, and it should be roughly equally likely that you fall into the left or right. And so the mixing time from that initialization should be poly. And lastly, I'll say critical Ising in dimensions 3 and 4 being poly. So thank you very much.
Maybe we limit to 2 or 3 because time is.
Okay, so I have a question on your second open problem. So if you begin from random initialization, won't it get trapped in the bottleneck? So why it will go to one of the phase?
Yeah, so essentially the random initialization should be kind of like there won't be any geometrical structure you start with because it looks very noisy. Over time, you'll start like getting clustering of blues next to each other and reds next to each other, and these fight. But one should take over in polynomial time. You shouldn't get like a kind of stable strip. And as long as you don't, then that would mean that you mix because you're equally likely to fall into the plus or minus by symmetry.
So how much of these arguments is restricted to Ising type model? Like suppose the state space is like 3, what it's like 3 bits or bigger. Like how much of this remains?
So in this picture, at high temperature up to the critical point is not known to be fast when I have 3 or more spins in dimension 3 or larger. In dimension 2, essentially everything in this picture holds for pots also, except for this D at least 5 part, but most of the rest holds. But as soon as I get to higher dimension, there will be a kind of, I don't know if this is clear, but there will be some gap where like beyond this, I know slow mixing, and up to here, I know fast mixing, but there's this region where I don't know that the Potts-Glauber dynamics is fast. Now, there's other algorithms. If you've heard of the Swenson-Wang algorithm, I didn't even get a chance to talk about something like that, but that are known to be fast for when I have 3 or more options instead of 2, when I don't have monotonicity. There's some things one can do, but there's definitely some of the arguments break.
Yeah, just speaking of that, maybe do you mind maybe also putting Swenson-Wang here on the phase diagram for Ising?
So for Ising, Swenson-Wang will be fast at high and low temperatures, and so fast, by fast I mean n log n, and it will be polynomial at criticality, but we don't know exactly what the polynomial is. And Guo and Jerem showed that the Ising Swenson-Wang is polynomial on all graphs at all temperatures.
So
in the talk, you mentioned that the folklore belief is not actually true. Do people know a concrete counter example, like or some lower bound results showing like
this
mixing
folklore belief, right? This one?
Yes.
Yeah, so here's a concrete example. In 3 dimensions, I take a cube and I initialize with an epsilon n width or an epsilon macroscopic width slab that's all red, and then everything else is blue. So this. So 10% of the volume of the box starts red, the other 90% starts blue. And this is a torus, let's say, or like no boundary. Then this will be this will take exponentially long to leave from.
Okay, thank you. Do we have some examples like in 2D Ising?
In 2D, I don't think there should be any. The worst thing will be polynomial. So there is no, that's not known, but in 2D, I think if I took the Markov chain and just restricted it to 1/2 of this picture, the mixing time from worst case initialization will actually be polynomial.
Okay, thank you so much.
Mm-hmm.
Okay, maybe one last question.
So towards your open problem 2, what will be the tools to do that? Because all those spectral graph, log Sobolev, or other things are very much agnostic to the initial condition. So.
Yes, correct. So I'm trying to develop more tools for addressing problems where you can handle like some initializations are fast, whereas others are not. And so one approach would be to study to say that the magnetization more or less does something like a random walk for a while. So let's if we were on a random regular graph or something, this might be easier. You want to say that the magnetization does a random walk for a while, and then once it's biased in one direction or the other, then you can actually prove that you're well within a phase, so you have fast mixing within the phase. Some kind of. But this
on the works you talked about, pretty much the only one that does a flavor like this is this GS22.
Yeah, that's right. I was going to mention briefly another work where we're able to show for random field Ising. So that's the Ising model where I put a random field on every box, on everything. This is another well-studied model in recent years. We're able to show that there's a regime where, or at least we are able to show like mixing from a warm start and use that to get a kind of simulated annealing algorithm for sampling from it. When it's like, if the field weren't there, it would be low temperature. So there's some long range order, but the field destroys it and helps.
Great. So let's thanks Professor Gheissari for the really wonderful tutorial.
Thanks so much.
And that concludes this morning's session.